One of my mentors, I once said, the more I learn about bulk solids, the less I know. And he said, don't worry, it's more difficult than rocket science. You'll eventually figure it all out. But what we're going to work on today is the skirt boards. Now I'm talking about just the skirt boards, the metal enclosure on the receiving belt. And we're going to talk about how CEMA goes about determining the width of your skirt boards and the height of your skirt boards and the length. I'm going to share with you several different methodologies that are out there, or rules of thumb, and we'll try to make some sense out of this. We're talking about reducing wear on your wear liners, which in turn, if your wear liner wears out, you'll have leakage in your transfer point. Well, that's a fugitive material. And we're also going to talk a little bit about the skirt board design for dust control. So let's get started. If I can. Skirt boards are not just a standalone item. It's not something that you design the rest of your conveyor and then you just plop the skirt boards on according to some rule. It really involves this whole section of the conveyor. Extremely important. We've covered this on other webinars, is you don't start loading until the belt is fully formed. And that'll give you a much better chance of your skirt boards working properly and not causing belt wear or damage. So typically the way you start out with the conveyor design is you know how many tons per hour. Let me see if I can get this thing working. You know where it's going, whether it's horizontal, vertical, or declining. You know your bulk material, how many kilograms per cubic meter or pounds per cubic foot, the lump size and the percentage of lumps, and the surcharge angle. Surcharge angle is that angle that the material forms on the belt after it's fully settled in, after it leaves the discharge area. So the design process is you usually pick a belt width and a trough angle and you run some numbers. And one of the key numbers that we're going to focus on is the cross-sectional area, because we want to manage that area to minimize how much material is rubbing on our skirt boards. And we have belt speed as a tool to help us with this. Obviously, if you want to get so many tons per hour and your cross-sectional area comes out a little bit too big for the belt speed you've chosen, you can speed up the belt and reduce the amount of material that would be rubbing on your wear liners. We're going to talk about CEMA methodology. CEMA uses these standard terms. This is your surcharge angle. So they idealize the material profile as a semicircular surface tangent to the surcharge angle. They use a standard center roll dimension. One of the nice things about their system is you can plug in any roll, any belt width, odd belt widths, odd roll diameters, odd troughing angles that you want. One key of what we're going to be talking about today is this standard belt edge. And it's calculated based on belt width. So in the example today, I think I use 36-inch belt most of the time, and that's about 2 7/8 inches. This is not your mistracking allowance. What this is when you leave the load zone and the belt sags a little bit between your widely spaced idlers, you don't want material falling off the belt. So we're going to talk a little bit more about that. CEMA uses a standard center roll, which is just an average of all the CEMA manufacturers' dimensions. In the CEMA manual, you'll see all of this complex geometry, really dimensionless ratios that are used. And this is a key in letting you put in your own dimensions for your center roller, your wing rollers, your belt, your trough angle, all of that. And what we're going to do is we're going to calculate what's called the standard cross-sectional area. And then we're going to put that into our skirt boards and see how high it rubs up on the walls. There's two key ratios we're interested in: the height of the material between our skirt boards, so that we know how high to make the skirt boards, and how much material is rubbing on the belt during operation. As far as the width goes, CEMA says 2/3 of the belt width. So if I have a 36-inch belt, I've got a 24-inch space between my skirt boards. And traditionally, that's the distance between the inside dimension of your skirt boards. But there's all kinds of different practices, rules of thumb, if you will, out there, down to half the belt width for really free-flowing materials, like finished cement, flows like water when it gets aerated. There's another one, 3 times the maximum lump size. Well, then that begs the question, what is your lump size? I don't know about you, but I've seen a lot of applications where they say it's a 4-inch minus lump, and then you have bowling ball size lumps coming through. So a lot of time you got to look at not just the nominal lump size, but what is the diagonal dimension, the longest dimension of your material. And keep in mind, if you're running through some kind of grizzly or screen, it could be a slab. It could be this 2.5 to 3 times longer than your nominal lump size. So typically this distance, what we call W sub S for skirt boards, is either 2/3 the belt width or something in between. And quite often the designer just picks that number without a lot of thought. But what we really need to look at is we need to calculate what's available here based on some allowances on the wings rollers of our belt. And what we get is there's actually 3 things we need to be concerned about. We need the standard edge distance. How much is the belt going to mistrack during normal operation? And then how thick is our whole sealing and wear liner system here? We add those all up, that's our allowance, which should give us a beginning point in our design to determine where our skirt boards would be placed. CEMA recommends calculating the standard area and then reducing it by 10 to 15%, and that's for surge loading under normal operations. That's one of the ways you can help reduce the wear on your wear liners if it's just handling a surge load against the sides of your skirt boards. So we can calculate the standard belt edge from that formula. Like I said, with a 36-inch belt, it's about 2 7/8. The mistracking allowance. CEMA has a mistracking allowance guide, and ISO also has some recommendations. So you can choose whichever way you want to go, but typically the CEMA system is based on standard CEMA components. So if you're using standard CEMA components, you'd want to look at the CEMA system. The 2 methods are practically identical. There's a few belt widths in the middle that don't match up exactly with ISO because we're matching the CEMA standard products. And you'll find generally it's the return idler that governs your mistracking, how much mistracking you can have before you get into structure or some other problem. You can use actual experience. This picture here in the center shows the belt has gotten itself up in a seam of the sealing system. And so the belt is no longer touching the idler. So you walk up and you see totally dirty wing idlers. It should be a clue that there's something seriously wrong. And if you don't have enough mistracking allowance, what happens universally, doesn't matter what sealing system you have, if that belt tracks out from underneath your seal, when it comes back, the belt edges have a tendency to curl up and it goes up inside of your shoe. And I've even seen it where it rolls the belt completely over. Over here on the right-hand side, you see somebody is price conscious, so they purchased this training device based on price. But if I walk up here, I notice that idler, there's no paint on it at all. So that should be an immediate clue that, hey, I've got a serious problem here. I've got to allow quite a bit for mistracking. And we've covered in other webinars, mistracking can be caused by off-center loading, misalignment of your components. It can even be caused by the wind or ice and snow, things of that nature. So it's very important to consider that in your skirtboard spacing. And then you've got the thickness of the sealing system. Whatever system you use, you need to know what that is so you can calculate how far along the trough edge of the belt before you can put your skirtboards. So this is another CEMA calculation that's in the design guide, which is called Belt Conveyors for Bulk Materials. And the latest edition was the 7th edition. But we're interested in this D sub MS, how much material is contacting here. And we also want to know how deep is the material, so we know where to put the top on cover on our skirtboards. When you see a small letter like D sub S, that indicates it's a dimensionless ratio, and you multiply that times your belt width to get the actual value. Same thing with the depth of material. There's a formula for that, and you can calculate that. One of the things you need to be concerned about when you're calculating area is what density do you use. The loose bulk density is what is normally given for a bulk solid. The vibrated bulk density would resemble more the density of the material once it's out in the conveying run and it's been compacted by going over multiple idlers, or it's been sitting in a bin for a long time and vibrated solid. The solid bulk density you need to, when you're looking at the impact of lumps on your belt, so you need to use the actual solid density. For example, limestone might come in at maybe 100 pounds per cubic foot, but the solid density is probably 220 pounds per cubic foot. So it makes a big difference on your impact. And then aerated density. When the material first hits the belt, it's got air in it. And part of your dust problem is that air, once that material consolidates, that air coming out and spreading dust. Most bulk solids like coal and aggregate, there's not much of a problem there. The air goes out pretty quickly. But some materials like wood chips, biomass, trash, when they're loaded on the belt, they tend to have a lot of air and they don't necessarily settle down as well. So that's critical to know that, so that your height is enough that you're not plugging up your chute. This can be as little as just a few percentage points, like with coal or aggregate, or it can be 40% for wood chips or something like that. And again, one of the easiest ways to get this information is just go take a look, measure your material, grab a bucket, and, fill it up carefully right off the conveyor and then figure out your bulk density that you're actually dealing with. Very critical that you know your material. So we're going to look at CEMA, what CEMA calls 100% or their standard area, and a completely full conveyor, edge to edge. Now, I know none of you ever have spillage on your conveyors, right? You never get that conveyor loaded edge to edge and stuff dribbling off the side. And then if you've got mistracking, then you've got a real mess. So we need to look at that edge to edge area. So here is using those formulas, I set up a little spreadsheet for Martin's projects people to use to kind of determine with their system where the wear liner is actually on the exterior of the skirtboards. How high up do they need to raise their skirtboard above the belt in order to avoid constant wear on it and let the sacrificial wear liner take it? So we looked at two areas: the CEMA standard loading, which is basically this where this belt edge, standard belt edge is, and then the semicircular top, and then look at what 2/3 belt width would do. What is this distance here where it's rubbing? That's the small d sum s times belt width equals the capital D sum s. Then we're also going to look at CEMA's area full, and there's a whole set of dimensionless formulas for this as well. And how high up on the skirt boards is that rub? So if my operating people have a tendency of trying to get caught up after some kind of an upset, or they're constantly loading it full, thinking they're helping production, usually that ends up in a big fugitive material mess, accelerated wear. In my experience is you never get caught up. You're much better off to run slow and steady at the design. But in this case, CEMA full edge to edge, the Martin Projects people want to keep their skirt board steel. And by the way, the skirt board we're talking about is the steel support on the sides, at least 4 inches above the belt. Standard running inch 1.6 inches. A lot of designers will actually try to design the capacity so that that point right here, this B sub WE point, is actually what we called our allowances. So they'll want that material not to just kissing the bottom of that wear liner, if anything. And that's one of the reasons CEMA recommends derating by 15%, 10 to 15%. And that's pretty standard practice. As far as how high to make the skirt boards, this is also from CEMA. I couldn't make heads or tails of it. This was in the very first CEMA book back in the 60s, and the chart's been basically the same since. I reached out to a few of my friends, and nobody really knows where these numbers come from. But we're going to take them just at face value for a 36-inch belt. So if I've got 2-inch lumps or down to real fine material, I'd look at about 11.7, say 12-inch high skirt board sides. If I've got 6-inch lumps, I'd be looking at 17 inches high, and so on. And these charts are in that the book, the design guide of CEMA. So, and this is a 36-inch belt I've drawn up here. So 2/3 of the belt width, 24 inches. And I've used 30-degree surcharge angle, which is a very steep surcharge angle. Most of your common bulk materials are 20 degrees. But this 30 degrees gives me more material in here, so I get my worst condition. This is where your lump size comes in. So there's also a CEMA chart here that says, all right, what belt width you're looking at. We're looking at 36 inches. And what's your lump size, maximum lump size you can convey on that belt. So you could theoretically go up to 12-inch lumps if there's very few lumps in your material and it's almost all fines, and you have a fairly low surcharge angle. In this case, I'm looking at all lumps, 30-degree surcharge angle, somewhere around 3.5 inches is the biggest lump that I should be conveying on that belt. So this is a case where you might look at this and say, oh, I better go back to my original calculations, run another calculation in terms of tonnage and belt speed and skirt board width. Try to get this point here right at the bottom of my wear liner. So just like the width, there's all kinds of rules out there. A lot of times these rules are developed because somebody puts in a conveyor and hey, it worked great. We put the skirt boards at 0.6 of the belt width and it worked great, but without really understanding why. So then that all of a sudden becomes the standard for the whole corporation forevermore. We're looking at this skirt board enclosure to do two things: contain the material until it's settled down and can form a nice uniform profile on the belt. But we're also looking at dust control. What are the things we can do with our skirt board design to help with dust control? Well, this first rule here says if you're going to put a dust pickup on it, you want to design those for an airspeed of 500 feet per minute. That doesn't really help us out too much. But if I go back to my 36-inch belt and I just picked a cross-sectional area of 2 square feet of material, then my height would be 1 foot. And that gives me the 500 feet per minute. Now, if I'm looking at passive dust control, where I'm just, I want the material, the dust to settle out as much as possible before it exits, then most of the rules are somewhere around 200 feet per minute or 1 meter per second is the maximum air velocity inside of your enclosure. So in this case, I would have to increase my height to 2.5 feet to get my airflow down to 200 feet per minute. This is the primary tool we use to determine the height of the skirt board. Then you've got to go back and check the CEMA chart to make sure that your lumps will pass through and everything else. So you've got to trade off in your design decision there. This is important. This next one, the chute work for air coming into your conveyor. When the material goes off of the head pulley into your chute and down onto your conveyor belt, the particles separate and it sucks air into your transfer point. And that's where your air problem comes from. So you want to limit the amount of air coming into your transfer point, and you do that with dust curtains where you're low on your discharge pulley, plugging up all your holes. Don't leave your inspection doors open. Put some kind of curtains where the belt exits the head pulley to just reduce that overall area. And then the last one is the cross-sectional area of your delivery chute. So we're talking about the chute that delivers material down to the receiving belt. And in this case, because this rule is given in metric, I went back and recalculated it. And my height would have to be about 1.1 meters in this case, or this particular given set of conveyor designs. So now we get into even more rules of thumb. So this is just the length of conveyor necessary to bring that material up to belt speed. So what we've got is the velocity of the belt minus the vertical velocity coming right out of the chute, divided by gravity times the coefficient of friction of the material on the belt, minus the tangent of the slope of your conveyor. Now, if you have a declining conveyor, that length of your skirt boards can get quite long to control that. On an incline or flat, typically this is real short, like a meter or less. Now, if we took a look at this example that I've got here, I've got my belt speed is 400 feet a minute. So I kind of back calculated if I had a 60-degree chute, how fast would that material have to be coming down that chute to be going 400 feet a minute when it hits the belt in the X direction. And I come up with a vertical velocity of 693 feet per minute. Now, you don't want to do that because that material is going to be coming down and just slamming on your belt. So this is one of the trade-offs designers make. And in this case, I said, well, I want to get fairly close to belt speed. So I'm going to figure my resultant vertical velocity here is going to be about 300 feet per minute. There's a lot of ways to do that. It's with the shape of your chute, the angle of your chute, those type of things, what kind of liner you have in your chute. But in that case, if my belt speed is 400, my vertical drop is 300, My coefficient of friction is 0.5, and I just pulled that out of there. That's on the high side of what you'll see. I only need 0.6 of a foot for that stuff to settle down on the belt, theoretically. Once again, the best evidence is go out and look at a similar situation. Well, back to the top of this chart, there's all kinds of rules, and unfortunately, there isn't much engineering or science behind these rules, and there still isn't. We'll talk about that a little bit later. What Martin uses is this, depending upon the belt speed and how much airflow is going through there. They'll use this formula. So 2 feet per 100 feet a minute past the impact zone. Remember, I said that that impact zone is usually less than a meter or so. So if we say 3 feet for that, plus 2 feet for every 100 feet per minute, I come up with about 8 feet. Plus, that's where my extension starts. That's after the impact zone. Now we're 12 feet here. So that's kind of, you see a lot of numbers falling in between that 8 to 12 foot range. That's kind of more or less a standard way to do it. Once again, I think practical experience is important. Then, of course, if you have multiple load points, there's a couple different ways to handle that. But some people will skirt the entire length with all the multiple load points, or some will have the skirt boards fairly narrow on the first load point, a little wider as they go down. That means you got to go back and calculate your feet on that first load point. If your skirts are narrow there, you don't want that filling up, plugging up your chute and causing unplanned downtime. So I realize it's probably all very confusing, but such is the life of a conveyor designer. There are no absolute answers. It's half engineering and half experience and skill that we're talking about. So you've got all these competing influences, plus you probably want to keep your price for your conveyor down to the minimum. The way I look at it is the 3 most important things are you want to deliver the throughput, how many tons per hour. That's why you purchased the conveyor. That's why you went through all this work, is to get that material from point A to point B. You want to do it as safely as possible. Now, this ties into fugitive materials. If you have a lot of spillage, a lot of dust, your maintenance is going to be higher. Your cleanup is going to be higher. Every time you go into the conveyor, whether it's running or not, your exposure to potential accidents is higher. So anything you can do to reduce the amount of fugitive materials really is directly related to safety. Life cycle costs, that's looking at the cost of your conveyor over its lifetime. We may have gone through these calculations, and our cross-sectional area says, well, for this 36-inch belt, it's going to be rubbing on my wear liners for 3 or 4 inches 24/7. So why don't I look at a 42-inch belt? Now the boss says, hold it. That costs too much. You got to you got to put 5 pounds of material in a 1 pound sack. And I don't care what you say, that it's not going to work. That's what you got to do, because that's all the money we have. That's a huge mistake. Huge mistake. I can't tell you how many conveyors I've seen that never get to this 100% design capacity because some of those types of decisions. Then you want to make it maintenance friendly. So let's say my calculation says, well, my skirt boards only need to be 6 inches high. Well, how are you going to get in there, put on a sealing system, get at your nuts and bolts inside of that trough belt? So that's one of the considerations. What's fabrication friendly, you'll find most of the standard skirt boards in bulk material handling at the load zone are about 12 inches high, unless you've got huge lumps. So, and that's a fabrication issue, standardization throughout your plant. You might have one bad conveyor that is the exception, but the rest of them can all be standardized. Access. Can your guys get at the wear liner? That's a critical point. Maintenance people spend roughly half of their time just getting to the item to be repaired. And I like to always look at upgradable. What I mean by that is we don't know where all these problems are going to occur on the conveyor. But you want to consider that in your design. For example, we may want to, in the future, speed this conveyor up, put more tons through it. So have you thought about that ahead of time? Made your skirt boards high enough to accomplish that? Something like that is what I mean by upgradable. So this is kind of how it all boils down. The width needs to be calculated, and it'll usually come out to less than 2/3 of the belt width. Your standard belt edge, your mistracking, and how thick your sealing system is, and then go check your lumps to make sure your lumps aren't going to plug up your skirt board. Your height, as I said, usually equal to 300 millimeters or 12 inches. And if you've got big lumps, then put your lump on top of the load so it clears. What we find is once you get out of that turbulent area, it's real typical then just to double the height of your skirt board system. Go back and calculate your air velocity to make sure you're in that 1 meter per second or 200 feet per minute zone. The length, I've been doing some research which indicates usually you want at least 3.6 meters when, and this is for dust control, not for turbulence or material settling. And your air at depth less than 1 meter per second or 200 feet per minute. Your skirt boards usually don't come very close to the belt. Typically 1 inch to 2 inches above the belt. There's really no need to get them right down next to the belt, except in unusual situations. You might have, you might be conveying real fine material like carbon black. In that case, you might want to get everything down real closer, but then you're usually talking about a smaller belt with a slower speed. So let's see. It's part of a system, so it's not just a standalone decision what you're going to do with your skirt boards. They need to be strong enough to handle the side pressure. Typically, that means they're going to be in the range of 4 to 10 millimeters thick, depending upon how much side pressure you have right at the loading point, and all that can be calculated. So, but a typical skirt board upright is 3/16 or 1/4 inch is what you would commonly see. And there are some suggestions out there based on belt width and tonnage. I think you can find those in the foundations books. What we really want to do for dust control is create recirculation. This has to do with dust curtains inside. I talked about minimizing induced air, so don't have a lot of openings in your chutes. Even around where the head pulley shaft goes through the chute, try to seal that up. Keep your inspection doors closed. And one thing to keep in mind is if you do decide that you're going to lengthen your transfer point for dust control, that friction of your sealing system and the friction of the material rubbing on your wear liners increases your power requirements. You got to go back and double check that. Now, if you got a conveyor, that's 300 feet long and it's got a 150 horsepower motor on it, it's not even going to see it. But if you skirt that conveyor the whole length, that's going to be a significant chunk of your power requirements. So this is some of the research I've been doing. on the length and the height for dust control. And this is a printout from a SolidWorks CFD program. And what I do is I inject a number of dust particles of different diameters from 100 microns down to 1 micron. And by manipulating the spacing and the height of this transfer point, I find where I create recirculation in my enclosure. We like to call this the settling zone or the stilling zone. In this case, I haven't allowed hardly anything for the material to come up to belt speed. But typically you would probably have a meter or so in there. And what this shows is I put 100 particles of each size in, and by optimally designing this, I'm only exhausting about 50 particles out of 600. So about 18% is being exhausted and the rest is being contained within. The other object is to keep that airspeed down. That's what all these blue lines are in, this 0 to 3 meters per second velocity. So what does that look like? We've set up the test to determine if the computer calculations are correct. This is Martin's Research Center. Here you'll see their external wearliner arrangement. In this case, the skirt boards are raised up, so the material doesn't rub on the skirt boards, but the wearliner is put on the outside. This is maintenance friendly. You can change your wearliner from the outside. You can adjust your skirting from the outside. In this case, I took this video. We injected some smoke. There's a shadow from a ladder here that kind of makes it hard to see, but there's only one dust curtain at the exit. And so we put some smoke in there, and you can see by just putting that one exit curtain on there and having it fairly close to the belt, all that smoke just exits the conveyor. So what I want to do is put enough resistance in here that I get that air recirculating. Another critical point as far as fugitive materials is put your last curtain inside of your enclosure. That stops what's called popcorn spillage, where that curtain, if it's on the very end here, that curtain tends to take loose particles and flip them off like popcorn coming off of your conveyor. Generally speaking, if you've got dry, dusty bulk materials, you want to err on the longer length of your skirt boards, and you want to err on more height than you would if you have material that's not dusty.